Hello everyone, welcome to the Advanced Heat Transfer course, and this is the lecture within the Advanced Heat Transfer course which deals with conductive and convective heat transfer modeling. Within ANSYS Fluent software we will see basic fundamentals related to convective and conductive heat transfer modeling, as well as how to set up a heat transfer model within ANSYS Fluent, and some case studies related to conductive and convective heat transfer. So let us begin with overview of this particular lecture. So first, before we begin into we go into details of modeling setup, we will see what is the energy equation that is used in order to solve a CFD heat transfer problem. The energy equation that is used is basically looks like this. So it has unsteady term, a convective term, a diffusion term, and species diffusion and viscous dissipation term. So this on the right, this is basically the convective heat transfer term, but on the right hand side, this is the conduction heat transfer term. Whereas this is the species diffusion term, the heat transfer because of species diffusion, and this is the viscous dissipation because of heat dissipated by the viscous effects. This is the viscous dissipation term, and this is the source term. So now this source term as such includes the heat of chemical reaction and any other volumetric heat source that we have defined. Also, E here that we are talking about is basically the total energy, which also includes enthalpy. Going ahead with detailed discussion of the viscous dissipation term, it is the energy created by viscous shear in the flow, and it is the energy source due to viscous dissipation, and it is taken by this particular term that we observed in the earlier equation also, this particular term. So it is already contained in the energy equation, and we can it is also called as viscous heating, and it is important when viscous shear in fluid is large. Example, in lubrication cases or in case of high velocity compressible flow, only in those cases we activate this term. It is often neglected. It is not included by default in segregated solver, but it is always included in case of coupled solver. But the use is basically only predominant in case of large viscous shear cases like lubrication, or in case of high velocity or compressible flows. Next is conduction. In conduction, the heat moves through a material, usually a solid or a viscous liquid, due to molecular action only. So in this case, in solids we have lattice vibration and flow of free electrons, which contributes towards conduction, whereas in liquids there is molecular collision and molecular diffusion, which contributes for conduction. And in gases there is again molecular collision and molecular diffusion, but the gases are rarely the molecules are rare in space. So basically this is the difference between conduction in solids, liquids, and gases. In case of modeling conduction, it is included in the energy equation term by the basic formulation of Fourier law, in which the heat flux is proportional to the temperature gradient. Q is equal to K delta T, and when we are trying to find out heat transfer rate, then we say Q is equal to minus Ka dt by dx. This is an example of conduction heat transfer from hot to cold side, and we are seeing the temperature gradient, temperature profile along x direction. Also, there is something called as conjugate heat transfer, which is referred to the ability to compute conduction of heat through solids coupled with the convective heat transfer in fluids. So this is like coupled heat transfer through the solids, and then the fluid around it also contributes by convection. So this coupled heat transfer is referred to as conjugate heat transfer, which involves conduction through solids and convection through fluids. There is a coupled boundary condition which is available for wall zones that separate two cell zones in fluid. We will see how to set this up in the coming slides. We can have both, like we can have solid zone as well as fluid zone, or both, which contain heat sources if we have to give any additional heat sources for heat formation or heat absorption. After studying the energy equation in detail, the entire energy equation, let us see a very specialized and simplified case of the energy equation, which is heat diffusion equation, which deals with only conduction. So taking our basis from the Fourier's law, if we perform a heat balance on a small volume of material, let's say this is the small volume of material at T temperature, conducting heat is coming in, and heat is also going out by conduction, and there is heat generation Q dot in this particular volume of material. In that case, this is the heat diffusion equation, which describes the heat conduction through this, which has a rate of that is an unsteady term or transient term. It also has a conduction term and a heat generation term. Notice that there are no convection terms because we are dealing with purely heat diffusion equation. In this case, we also have a property called thermal diffusivity, which is K by rho C. And this is the heat conduction equation, which is a simplified case of the energy equation, to complete energy equation. Now, once we have established our base with respect to the with respect to the energy equation and the theoretical and mathematical background of modeling heat transfer, let us see how do we set up a simple heat transfer model in Fluent. What are the generalized steps that are involved in setting up a heat transfer model in Fluent? The first step is basically to go to problem setup, models, energy, and turn the energy equation on. This is the first step to model any type of heat transfer problem. For this, we go to models, we go to energy equation, and we turn it on by clicking here. After that, the second step is operating conditions. We go to the operating conditions panel, and here we set the operating temperature, which is given here, which defines what is the operating temperature used for various heat transfer calculations. And we also set the density formulation, which is given here, which is actually the operating density also for various density calculations based on temperature. So these are the two critical setup which matter in heat transfer, which is operating temperature and operating density. This is the second step. Once we are done with the second step, the third step is to set up boundary conditions. For that, we go to each boundary condition panel of each boundaries that are that matter to us with respect to heat transfer. In that, we set the boundary conditions on cell zones as well as boundary zones. The most critical are wall temperatures, which are shown here, or wall boundary conditions on different walls. An example here for one of the wall is shown, and we can set up different boundary conditions, which we will discuss in detail when we discuss boundary conditions in detail related to heat transfer.